thank you. So, as I said, I am Bassah Bakki from Rojava University, and my studies about carbon quantum dust membrane for hydrogen sulfide separation from natural gas. As we know, natural gas is a critical energy source and is playing an important role in the global economy, and it's used for as a fuel for generating electric power, feedstock, and feedstock of production of many chemical products. As we know, natural gas, it's a mixture of hydrocarbons such as methane, ethane, propane, and some condensate. It also contains a significant amounts of hydrogen sulfide and carbon dioxide. Hydrogen sulfide is a colorless gas, and it's corrosive for equipment and pipelines and all the storage facilities that is being used. Also, it is a very toxic gas. So before natural gas can be used or be injected in pipeline, we need to separate or remove hydrogen sulfide from natural gas. Our study objective is developing and fabricating polymer membrane (PVDF) incorporating carbon quantum dots sensed from agro waste, specifically pomegranate peel powder for the efficient separation of hydrogen sulfide. The advantage of using carbon quantum dots is that carbon quantum dots have many properties. It's small size, chemical stable, and non-toxic. Also, carbon quantum dots are rich in functional groups such as COH, NH2, and OH. Also, the main thing here is that carbon quantum dots can enhance the mechanical and chemical properties of the membrane and can be sensed in a very simple way without releasing any toxic byproducts or using complex equipment, because as we said, it's from agro waste. The methodology of our study, it was like this. First, preparation steps of carbon quantum dots. Some easy steps we can say. Fresh pomegranate peels, we had to clean them and dry them. After that, grinding the peels to powder. This powder, we carbonized it for 2 hours at 200 Celsius, and then the carbonized powder, we had 1 gram of this carbonized powder and mix it with 100 millim of distilled water. This solution, we sonicated it for 50 minutes in ultrasonics, and then the solution, we put it in autoclave. This autoclave, we heated this solution for 10 hours at 100 Celsius. Then the resulted solution, we needed to filtrate it to get rid of the dust, waste, or any solid impurities. Then the resulted solution for further treatment, it was subjected to centrifuge, and thus we could obtain our carbon quantum dot solution. The next step in our study, it was preparation the membrane, and using the solution carbon quantum dots that we obtained in preparing this membrane. I will just brief the steps of the membrane preparation. It was like this. The polymer solution, we had to mix them for 8 hours, and then we left them for 24 hours in order to remove the bubbles from the public solution. The poly separate, we fix it on a glass plate, and then we casted our membrane film by using a film applicator with a thickness of 200 micron. Then the glass, we immerse it in a distilled water coagulation bath. In those procedures, we get 4 types of membrane. Of course, the main component of the membrane polymer was PVDF, and carbon quantum dots. The membranes were like this: G1, 0 carbon quantum dots. We didn't use any carbon quantum dots. It was blank. And G2, 0.1, G3, 0.2, G4, 0.5. The membrane we prepared and the carbon quantum dots were characterized by using FTR, SEM, HTM, and contact angle mechanical testing. The mechanical testing showed that carbon quantum dots membranes, especially G3, G4, were with increased carbon quantum concentration, showed superior mechanical properties. That's due to the presence of carbon quantum dots that facilitated greater diffusion between the solvent and the water, which enhanced the porous extraction and led to improved tensile strength and mechanical properties overall. After that, we had some parameters tested, some parameters to study the performance of our membrane. The first parameter was gas permeation in two situations. The first situation was using natural gas without the presence of CO2. Without CO2, the three membranes, G2, G3, and G4, which contain carbon quantum dots, showed effectively rejection of hydrogen sulfide, while the membrane G1 without carbon quantum dots showed no selectivity for the rejection. In the case 2, where we used the hydrogen sulfide, hydrogen sulfide and CO2 in the mixture of the hydrocarbons of natural gas, actually it showed that the selectivity of the G3 and G4 decreased, while the selectivity of the G1 and G2 slightly increased. Selectivity of the rejection. The next parameter was studying the effect of pressure on the membrane performance. Overall, increasing the pressure increased the selectivity of the hydrogen sulfide rejection. That's because we know increasing the pressure facilitated the accumulation of hydrogen sulfide and leads to the plasticization, increasing solubility, and in the end plasticization. So that increasing the pressure decreases the selectivity, while decreasing the pressure through opening the valve rejection of the H2S increased the selectivity. So we came to the conclusion that increasing pressure decreased the selectivity of hydrogen sulfide rejection. We also studied the effect of carbon quantum dot concentration on the membrane performance. Actually, the three membranes with carbon quantum dots, G2, G3, G4, showed a superior separation efficiency for hydrogen sulfide separation, and they reached equilibrium after 2 hours, while G1 without carbon quantum dots showed lower performance and reached equilibrium within 3 hours. And that's, because of the nanoparticles alter membrane structure, so that and enhance the mechanical. Okay, I will complete it in 1 minute. The last parameter was if studying the effect of flow rate, and as it shows on the figure, is that increasing the gas flow rate increase the percentage separation of hydrogen sulfide separation. The conclusion, as we said, carbon quantum dots sensed from agricultural waste enhance the mechanical properties of the membrane and the separation percentage of H2S, and also it's a very we can say approach, eco-friendly approach to be applied in the demonstrate strong potential for industrial application. We just recommend that studying the variety of effect of varying thermal treatment temperature on the membrane performance and application of multi-stage membrane system should be explored too. Further research would be also focused on optimizing both scalability and long-term stability. In the end, I would like to thanks the Prof. Hiba and Dr. Samah and Dr. Heather Safia for their support and supervision on this study, and Rojava University and Syria Gas Company for their support and providing resource. Thank you so much, and sorry for taking more time.